Hi everybody. So in this video what we're going to do is we're going to introduce a couple of new gates. So the name of these gates are XOR and XNOR. What that stands for is exclusive, so exclusive OR and exclusive NOR. Alright, now the gates themselves have somewhat of a similar look to them. So if we draw an OR, it looks like this. If we draw an exclusive OR, it looks like this. See how we have this extra curved part before the gate? All right. Now, if we're looking at exclusive OR, it has kind of an interesting truth table to it. So if we have our inputs of X and Y and our outputs of Z, an OR gate, the output is a 1 whenever any of the inputs are 1. So if it's X or Y or both. The difference with an XOR is that its output, Z, is a 1 when X is a 1 or Y is a 1, but not if they're both 1. Basically, it tells you if the inputs are different. So when X and Y are both zeros, they're both off, our output is a 0. And if they're both on, our output is a 0. But in the situations here and here, where our inputs are different, that is where an XOR actually would give you a 1 as an output. All right. Our XNOR, on the other hand, so remember, a NOR gate looks like this. This is NOR. XNOR has a similar kind of setup. We have that curve in the front, and then we have our NOR gate after it. Our XNOR gate, provided X and Y are inputs and Z's are output, actually acts almost the exact opposite of our XOR gate. So, where XOR told us if our inputs were different, our XNOR gate tells us when they're the same. So, we get an on output when both X and Y are 0 or when both X and Y are 1. Otherwise, the output of the gate is off. So that's our XNOR gate. All right. These are the two gates that we're going to be looking at today. Now, what can we do with these things? So we do have a little bit of AOI logic that can be simplified with them. For example, if I had a function that was equal to x, y naught, z, or x naught, y, z, and I came down here and took the z out. So I'm going to use my Boolean algebra and take a z out, and I get x, y naught, or x naught, y. So what is this? This is what we would get with a NOR gate. So for example, let's go back one more, sorry. Here, there we are. So see what we have right here? This is x naught y, and this is x y naught. This is exactly what we would expect with an XOR gate. Now, we could write this, x naught y or x y naught, but there's actually a simplified version of writing it. You can say x, and this is the symbol for exclusive OR, is sort of the plus OR symbol inside of a circle, y. All right, so when we come back over here, what we can do is simplify this part, and we'll just end up with X XOR Y. So when we went to draw this gate, we could actually just say X, Y, Z. The X and Y are XORed together, and then ANDed onto Z, which is a much simpler way of drawing it, because otherwise you would not be able to draw that with only two gates. All right. So where does all this come in handy? Well, the most obvious place in electronics is in what's called an adder, when you're using a circuit to add together numbers. Now, since we're in binary, there's only a few numbers we can add together. 0 and 0, 0 and 1, 1 and 0, and 1 and 1. When we add 1 and 1 together, we get 2, which is 1, 0. Notice, if I look at the XOR truth table, zero and 0 added together is 0. So almost imagine little pluses in here. 0 and 0 added together is 0. 0 and 1 added together is 1. 1 and 0 added together is 1. And 1 and 1 added together, if we look just at the first column here, is 0. All right. So we can kind of see how this would be useful for adding together binary digits. And in fact, that's going to let us get to our first circuit, is something called a half adder. Now, a half adder is a circuit, and I'm just going to draw a square to represent it, and you put in two numbers. We'll just call them A and B, and these are binary numbers, zeros or ones, and we get out a sum. But we also, if we're going to add things together, need to contend with this possibility, all right? Because 1 plus 1 and 0 plus 0 are not the same thing. So we also need to have a carry-out digit, because when we add 1 and 1 together, we get 2, which means we have a 0 carry the 1. So we have to account for that carry digit. So we have a carry-out digit. So if we want to make a half adder, the most direct way of doing it is to consider what the truth table looks like. So we have inputs, A and B. We have a sum as one of our outputs, and we have a carry-out digit as one of our outputs. So let's make our truth table. So if we take 0 plus 0, the sum is 0, and we don't have any carry-out digit. 0 plus 1, the sum is 1, and we don't have a carry-out digit. 1 plus 0 is 1, and we have no carry-out digit. And 1 plus 1 is 2, which is a 0 with a carry-out digit. So what we can see here is the sum is just A XORed to B, and our carry-out digit, notice it's only a 1 when both the digits are 1, so our carry-out is just A ANDed to B. So when we imagined our circuit as just a box with A and B and our sum and carry-out, what's actually going on in there? Well, A and B, that goes to our sum digit, that goes to our carry-out digit. All right, so we have our XOR here and an AND gate here. And that's how we can make a half adder. Now, a half adder has limitations, all right? Let's imagine we're adding together a binary number. All right, so let's say we've got 1, 0, 1, 1, and 0, 1, 1, 0. All right, this first column right here, all right, we often call this column 0. So we would say that this is A0 and B0. That corresponds to the A and B up here. There only can ever be an A and a B, all right? We add them together, we end up with a sum digit, all's well and good. We might have a carry-out digit. Now, if it so happened we did have a carry-out digit, like let's say this wasn't a 0, let's say it was a 1, so we would end up with a 0 here and a carry-out digit. Now what happens? We can't use a half adder to add up this column because not only do we have inputs of A and B, we also have this carry digit to contend with. If you look at the half adder, is there anywhere to have a carry in digit? No. So a half adder can only work in this first column here. So we can use a half adder for that one. Any of these other columns, so this is column 0, column 1, column 2, column 3. Any of these other columns, 1, 2, 3, any of them past column 0 could have a carry-in digit. And we have to be able to account for that possibility. So what we do instead is we have to look at a full adder. Now, a full adder is a different circuit and we have to be able to take still an A and a B. And when we say an A and a B, we say anything in this row is column A, anything here is column B, and it has to be able to have a carry in digit. Now when we say carry in, how's it different than carry out? Well, this 1 carried out from column 2 and into column 1. So the carry out from 0, so the carry out from 0 is the carry in to column 1, all right? And the carry out from column 1 is the carry into column 2, the carry out from column 2 is the carry into column 3, so on. All right, but we have to be able to account for that now. And what else do we need? Well, we still need to have a sum digit, a digit that goes on the bottom, and if there's a carry out, we need to be able to tend for that. All right, so basically what we're doing is we're adding 3 digits together here, because if you look in this row, in mathematics, when we have a carry-in digit, we just add it to the other numbers. So we're adding 3 digits together. So our inputs now are A, B, and our carry-in digit. Our outputs is a sum and a carry-out digit. So we'll go ahead and make our truth table. All right, I like to put a little line here. It just helps me keep all of my rows straight. So if I add 0 plus 0 plus 0, my sum is 0 and there's no carry out digit. If I add 0 plus 0 plus 1, I get 1 and no carry out digit, and you guys can kind of see how this goes, so I'm just going to go ahead and do it. Now on the very last one, I add 1 plus 1 plus 1, which is 3, and remember binary 3 is 1, 1, So my sum digit is 1 and my carryout digit's 1. All right. So how do I turn this into a circuit I can work with? Well, we're going to actually make a K-map here. All right, and we'll make our K-map for, let's start with our carryout. And if we fill in all of our numbers, so 0, 0, 1, 0, 0, 0, oh, 0, 0, 0, 0, 0, 0, 1, sorry, 0, 0, 0, 1, 1, or 0, blah, 0, 1, 1, 1, 0, 1, 1, 1. All right, and I can group this together. And what I find is that my carry out is AB or BC or AC. And that makes sense if we think about it. Basically what we're saying is we're going to carry out a digit if any two numbers are ones. So if A and B are ones, we'll have a carry out. And that makes sense because it adds up to 2. If B and C are both ones, they add up to 2. We have a carry out. If A and C are both 1, we have a carry out. So that makes sense. Now, the truth table for the sum digit is ugly. All right, so let's go ahead and look at it real quick. It actually ends up looking like this. And there is no good grouping. All right, now I'm going to save you a little bit of Boolean algebra here. If I would write this out, I'd get A naught, B naught, C, or A naught, B, C naught, or A, B, C naught, or A, B naught, C naught. There we go. And I could use the Boolean algebra just like I did earlier to simplify this. And actually what I would get is kind of an interesting result. I get A XOR B XOR C. All right. So what that tells us is when we're all said and done, if we want to make a full adder, so what goes on in this full adder? Remember we had A, B, and a carry in digit. We had a sum and a carry out digit. What goes on in there? Well, the sum, like we said right here, is all of these XOR together. And the carry out digit is AB or BC or AC. All right, so A XOR B XOR C, AB or B C. When I say C, I'm saying carry in, or A carry in. All right, so that is what goes in a full adder. It's significantly more complex than the half adder, and that's why, even though you can only use it in the very first column, that 0 column on a circuit, why you would still use 1/2 adder when you're adding digits together. So if I was adding 4 digits together, I would have, so this is A0 plus B0, A1, B1, all right, so if I was adding these together, to add A0 and B0 together, I would go ahead and use that half adder. So I'd use A0 and B0, and they would both go into a half adder. I'm not going to draw all the circuit stuff. And I would have a sum digit. This would be sum 0. That would go here. And I might have a carry out 0. And that would be up here. My carry out 0, which is also my carry in 1. All right, and so this would come around, and I would use A1 and B1 and my carry in 1, and those would go into a full adder, and I would get the sum for column 1 out, and I would have a carry out digit. This would be carry out from column 1, which becomes the carry in for column 2, and I'd use A2 and B2, and those would all go into another full adder, and I'd have output sum 2, and that would go here. You guys get the idea. Let's get rid of that column. And now my last digit here, this carry out 2, where does it go? There's nothing else. There's only columns 0, 1, and 2. So where does carry out 2 go? Well, it would normally go up here, carry out 2. And what happens when there's no numbers here? Well, you're adding it together, so it just goes here. So that's carry out 2. So that's how you could add together 2 3-digit binary numbers, and you could have up to a 4-digit solution by using half and full adders.